Bismillahirrahmanirrahim. I welcome you to the 27th lecture for the series of lectures on advanced computer architecture. Today, after a brief review of what we discussed last time, we will discuss the cache performance matrix, the cache design techniques, and different attributes which determines the performance of a cache. Last time we discussed that in order to obtain high-speed storage at the cheapest cost per byte, different types of memory modules are organized in a hierarchy which is based on the concepts of number one, caching, and number two, locality. We discussed that the concept of caching states that a small, fastest, and most expensive storage be used as the staging area, or say a temporary storage, to store frequently used subset of the data or the instructions from the relatively cheaper, larger, and slower memory. And this is done to avoid having to go to the costly memory every time the information is needed. Therefore, we found that static random access memory is used as a cache memory, and it provides the fastest storage for bulk of information. Secondly, we discussed the principle of locality, which states that to obtain data or instructions of a program, the processor accesses a relatively small portion of the address space at any instant of time. Therefore, the information in this area should be available in the fastest memory, which is placed closest to the processor. However, we also talked about different types of locality. The two important types of locality are the temporal locality and the spatial locality. Temporal locality is the locality in time which says that if an item is referenced, it will be referenced again very soon. Whereas the spatial locality states that it is a locality in space, which means that if an item is referenced, then the items whose address are close by will tend to be referenced soon. Now, in order to take advantages of the temporal locality, we said that the memory hierarchy will keep more recently accessed data items closer to the processor, because chances are the processor will access them again very soon. Whereas in order to take the advantages of the special locality, not only do we move the items that has just been accessed closer to the processor, but we also move the data items that are adjacent to themselves. Following this discussion, we discussed the cache devices. Here we notice that cache device is a small, static, random access memory which is made directly accessible to the processor. A cache sits between the normal, or say the main memory, and the CPU as the data and instruction caches, and these caches may be located either onto the CPU chip or as an external module close to the CPU chip. The data transfer between cache and CPU and the cache and main memory is performed by a hardware as part of the cache known as the cache controller. The cache and the main memory is organized in equal-sized blocks. We also found that an address tag is associated with each cache block that defines the relationship of the cache block with the higher level memory, say with the main memory. We also observed that the data transfer between the CPU and caches take place as the word transfer, and the data transfer between the cache and the main memory takes place as the block transfer. Then we talked about the operation of a cache, where we found that for data transfer between the cache and the main memory, the CPU requests the contents of the main memory location, whereas the controller checks the cache blocks for this data or instruction. If this data or instruction is found in the cache, we call this a hit operation. Then it reads the data or the instruction from the cache very fast, and this in fact provides the required information to the CPU at the speed of the fastest memory. Whereas if the data or instruction is not found in the cache, then it is said to be a miss operation, and then the controller reads the required block from the main memory to the cache, and then it delivers the required object or the required data or instruction from the cache to the CPU. So this shows how a cache is interfaced with the main memory, and the cache controller controls the operation of a cache. Now, before we proceed further with the design of the cache, let us discuss how the cache memory affects the overall performance of the system. In order to discuss this in details, we have to understand some basic terminologies, that is the miss rate, the miss penalty, and the average access time. These are the three major trade-offs for the cache memory performance. Miss rate is defined as the fraction of memory access that are not found in the level K memory. This actually means that out of the total memory requests made, how many requests have been missed. So we can define the miss rate as it is equal to the ratio of the miss instructions out of the total memory accesses. So this is equal to the number of misses divided by the total number of memory accesses. Now you can note that as the hit rate is defined as the fraction of memory accesses that are found in the cache. So this means that we can say that the miss rate is in fact equal to 1 minus the hit rate, or we can develop relationships between the hit rate and the miss rate from this. Whereas the miss penalty is the memory stall cycles, that is the number of cycles a CPU is stalled for a memory access, and it is determined by the sum of these two quantities, that is the number of cycles, or say the cycle time, to replace a block in the cache. And the second is number of cycles or the total time to deliver the block or the required object to the processor. The third performance matrix is the average access time. The average access time is basically the measure of the average time which is required or which is spent to access the data or instruction. And it is therefore defined as equal to the sum of the hit time multiplied by the hit rate plus the miss penalty multiplied by the miss rate. Now, considering these three basic attributes, let us find out with the help of some examples the relationship between all these multiplied by the miss rate multiplied by the miss penalty can be calculated. The performance of a CPU is basically the product of clock cycle times and sum of CPU clock cycles and the memory stall cycles. This actually means that we can express the CPU execution time by an expression which is written as shown over here, that is the product of the sum of clock cycles plus the memory stall cycles and the clock cycle time. Here the memory stall cycles are equal to the number of misses multiplied by the miss penalty, which can be written as it is equal to instruction count multiplied by number of misses per instructions overall multiplied by the miss penalty, where the misses per instruction can be expressed as the memory accesses per instructions multiplied by the miss rate. So this gives us the final expression for the memory stall cycles, as it is equal to the product of instruction count, memory accesses per instruction, miss rate, and miss penalty. Here, note that this expression is an approximation because the number of cycles for the memory read and for the memory write in reality may be different. Moreover, the miss penalty for the read or the write operation may also be different. Therefore, a more accurate expression can be written as the memory stall clock cycles is equal to the sum of the memory read stall cycles and the memory write stall cycles. Now, let us consider an example to analyze the cache performance. In this example, let us assume that a computer has clock cycles per instruction equal to 1 when all memory accesses are hit, and the only data accesses are load store accesses, and these accesses are 50% of the total instructions. Now, if the miss rate is 2% and the miss penalty is 25 clock cycles, then let us find out how much faster the computer will be if all instructions are hit. For this purpose, let us first of all calculate the execution time for all hit operations. The execution time for all hit operations is equal to the instruction count multiplied by the clock cycles per instruction multiplied by the cycle time, which is equal to IC multiplied by 1 multiplied by cycle time. Whereas the CPU execution time with the real cache is equal to the CPU execution time and the memory stall time due to the presence of the cache. Now, the memory stall cycles due to cache can be determined as it is equal to the instruction count multiplied by the instruction access plus data access per instruction. Now, by substituting the given data in this expression, we find that the memory stall cycles equal to the instruction count multiplied by 1.5, which is equal to 1 for the instruction access and 0. Which is the 50% data access, multiplied by the miss rate, which is equal to 0.02 or 2%, and the miss penalty, which is equal to 25 clock cycles. So it results in the memory stall cycles equal to instruction count multiplied by 0.75. Now, adding these two values as the one which we determined earlier and this value, it results in the total CPU execution time equal to 1.75 multiplied by the instruction count multiplied by the cycle time. Now, if we find the ratio of the execution time of the system without cache and with cache, it shows that it results in that the computer with no cache misses is 1.7 times faster than the computer with cache misses as described in this example. Now let us discuss how the block size trade-offs the miss rate, miss penalty, and average access time. First of all, let us see how the miss rate changes in the size of each block of the cache. Here in this graph, you can see that when the block size is very small, the miss rate is very high. It is quite obvious. When the block size is very small, it will be holding very small amount of data or small number of instructions. Hence, it cannot completely utilize the concepts of spatial locality or the temporal locality. Therefore, the miss rate is very high. However, when we increase the size of the block with the larger block size, the miss rate is reduced because it starts taking the advantages of the spatial locality. Here you can see that if the block size is too big relative to the cache size, then the miss rate will once again go up, because in this particular case there will be too few cache blocks available and it cannot hold different types of data or instructions. Typical example of too big block size can be when we assume that the block size is equal to the cache size. That is, the cache has only one block. In this particular situation, the miss rate probably will go to infinity. It is true that if an item is accessed, it is likely that it will be accessed again soon, but probably not as soon as the very next. Therefore, the next access will cause a miss again. And if this process is to be repeated, this means that the miss rate will go to infinity, or it will be very high. And what we will end up is loading data into the cache, but the data will be forced out by another cache miss before we have a chance to use it again. This particular situation is referred to as the ping pong situation. That is, the data is acting like a ping pong ball which is bouncing in and out of the cache. As we have noticed that the miss rate is very high when the block size is small, and it is also very high when the block size is too large. However, while talking about the performance of a cache, the miss rate is not the only parameter. Rather, we have to take into consideration the effect of the miss penalty, where, as we defined earlier, the miss penalty is in fact the total number of stall cycles which are required to provide the data in the cache in case of a miss operation. Here, let us consider this graph to study how the miss penalty changes with the change in the block size. Here you can see that as the block size increases, the miss penalty will go up. It is quite obvious because the block, when it gets larger, it will take you longer to fill it up, which means that if the block size is increased, the number of stall cycles to fill a block, that will also increase. Now we have noticed that the bigger block size does not always work. Rather, as the block size increases, assuming that the cache size is constant, the miss rate will drop rapidly at the beginning, and this is due to the spatial locality. However, once the block size passes a certain point, the miss rate eventually starts going up. Now, let us combine these two effects, that is, the effect for miss rate and the effect for miss penalty onto the performance, and see how the block size affects the average access time, which is really the more important performance metric than the miss rate or the miss penalty considered individually. While combining these two curves, let us note that the result of merger of these curves for miss rate and miss penalty, the average access time will go down initially because the miss rate is dropping much faster than the increase in the miss penalty. But eventually, as we keep on increasing the block size, the average access time can go up rapidly, because not only is the miss penalty increasing, the miss rate is also increasing at this stage. So this shows that the combined effect of the miss penalty and miss rate is much high onto the average access time, and eventually the average access time also starts increasing when we increase the block size beyond a certain point. So this graph, which results in the merger of the graph corresponding to the miss rate and miss penalty with respect to the block size, it shows that there is a critical position when, or the critical value of the block size when the average access time is minimum. And we usually use this block size for our normal operation. Now, with this much discussion about the performance matrices for the cache, the block size trade-offs, let us have a look how we can design a cache. For this purpose, we can say that cache is basically a memory element which has got some data and address lines, and it also contains some storage media to hold the contents of the block, as well as some tag values associated with each block. In order to design a cache, we have to define a set of operations which must be supported by the cache. These operations are the read operation and the write operation, where the read operation results in the memory read from physical address and make this data available to the cache. And memory write means it writes data to the physical memory. Furthermore, we also have to determine the relationship between the physical address and the cache address. And finally, we design the cache data path and cache controller. Here, this block diagram shows the interface between the cache data path and the cache controller. The cache data path has its inputs as the address lines, the data in and data out lines, whereas the cache controller generates the control signals and it obtains the control information as read or write active and the wait signals when it is to be in the stall position. So now let us discuss how we can organize a cache into different categories for actual design purposes. A cache can be organized in 3 different ways based on the block placement policy. The block placement policy defines where a block from main or say physical memory be placed in the cache. There exist 3 different block placement policies, namely the direct mapped, fully associative mapped, and set associative mapped. Let us first of all discuss what is direct mapped cache organization. A direct map cache organization is one where each block has only one place where it can appear in the cache. For example, if we look into this block diagram, you can see that we are assuming that a computer uses 16 MB main memory and 1 MB cache. These memories are organized into number of blocks and each block is of 4 bytes in size. That is, the main memory has got 1 M blocks, that is 1 meg blocks, and the cache is organized in 256 K blocks and each block is of 4 bytes. Each block in the main memory as well as in the cache is addressed by a line number. Now, in order to understand the placement policy, the main memory is logically divided into 16 sections, each of 256 K blocks, that is, each section is equal in size to the size of the cache, and each section is represented by a tag number which ranges from 00 up to FF hex. Here, each block of the main memory maps to only one cache line. That is, for example, you can see that the block number at line number 339C hex from any of the 16 sections in the main memory must be placed at the line number 0C E7 hex with corresponding tag in the cache. This shows that the direct mapping is given by the block address, mod, block number in the cache. For example, here, whether it is in the first section where the address is 00339C hex, its modulus with 3FFFF gives us a value equal to 0C E7. And similarly, the block address 16 339C hex is also placed in the cache at the address 0C E7 hex. This direct addressing can be described in further detail with the help of this address structure. Here you can see that the physical memory address, which in this example is of 24 bits. These 24 bits are divided into 3 fields, namely the word field, or the second is the line or the slot or the index field, and the third one is the tag field. The word field is basically defining what is the word size, and the word size is of 4 bytes in this case. Therefore, any of these 4 bytes can be addressed by a 2-bit value. So the remaining 22 bits are known as the block identifiers for the main memory, whereas these 24 bits are further divided into 2 sections, that is 8-bit tag value and 14-bit slot or line or index value. Here note that no 2 blocks in the same line or with the same index value have the same tag field. So this means that we can clearly identify the tag value by the uppermost bits of the address, and the index value can be defined by the middle field, and the byte location within one block or one line of the cache can be defined by the first field. In order to further understand the address translation, let us reconsider our previous example of main memory of 4 gigabyte. That is, it has got an address field of 32 bits. This memory is divided into blocks of size 32 bytes each, and this memory is associated with a cache of 1K byte. The cache is also divided into 32 lines or 32 blocks, and each block is of 32 bytes. Here you can see that the 32-bit address field has been divided into 3 sections. The first section, that is from bit 0 to bit 4, it identifies the bytes within a block, whereas the bit 5 to 9 indicate the block index or the cache index, whereas the 22-bit field from bit 10 to 31, they indicate the cache tag value. The direct map cache is simple, inexpensive, and it offers fixed location for a given block. So if a program accesses 2 blocks that map to the same line repeatedly, cache misses will be very, very high. However, disadvantage of the direct map cache. Disadvantage has been overcome in the other design, which is referred to as the associative mapping. The associative mapping is one where we forget about the cache index and we can place any block of the main memory anywhere in the cache. Here we don't even have to bother to use any address bit as the cache index. We just store all the upper bits of the address except the byte select bits that is associated with the cache block as the cache tag and have one comparator for every entry. Here, the address is sent to all entries at once and compared in parallel, and only the one that matches are sent to the output. This is called an associative lookup. Needless to say that it is very hardware intensive, but usually fully associative caches are limited to small number of entries, for example, less than 64. Since we are doing only mapping with the cache index, we will never push any other item out of the cache because multiple memory locations map to the same cache location. Therefore, by definition, conflict miss is 0 for a fully associative cache. This, however, does not mean that the overall miss rate will go to 0. Assume we have 64 entries here. The first 64 items will be accessed and they can fit into it. But when we try to bring the 65th item, we will need to throw away one of them which is already existing in order to make room for the new item. This, in fact, gives rise to another type of cache miss, which is known as the capacity miss. That is, when the cache is completely full, it does not have any additional space to bring new data or instruction in, then we have to throw away some existing information from some block of the memory. This type of cache miss is referred to as the capacity miss. However, now we will discuss the third type of mapping known as the set associative mapping, which in fact makes use of the merits of both the direct mapped as well as the fully associative mapped memory. Set associative addressing is one where the cache is divided into a number of sets, where a set is a group of blocks in the cache at each index value. Here, a block is first mapped onto a set, that is, it is mapped at an index value and then it can be placed anywhere within that set. For example, if we have got two-way set associative cache, then two values at the same index can be placed into this cache. Let us consider this example of two-way set associative cache. Here, two cache entries are possible for each index, that is, two direct addressed caches are working in parallel here. Here you can see that a direct map cache is on the left-hand side as well as on the right-hand side of the line showing the cache index. These two sets, they are combined with the help of a multiplexer. The value from any one of the set, from the same index location can be made available at the output of the multiplexer. Now let us study the working of this two-way set associative cache. Here you can see that the cache index selects a set from the cache. The two tags in the set are compared in parallel with the upper bits of the memory address. If neither tag matches the incoming address tag, we have a cache miss. Otherwise, we have a cache hit, and we will select the data on the side where the tag number matches. This is simple enough. However, it has got some disadvantages. Let us see what are those disadvantages of the set associative cache. The demerits or disadvantages of set associative cache are that an n-way set associative cache will need n comparator instead of just one comparator as it is used in the case of direct mapped cache. Furthermore, the set associative cache includes a multiplexer, and this multiplexer slows down the operation because of the delay introduced in selecting the block from a particular set. Finally, for n-way set associative cache, the data will be available after the hit or miss signal becomes valid, because the hit or miss is needed to control the data multiplexer. However, as you can see here, that for direct map cache, that is everything before the multiplexer on the right or the left, the cache block will be available before the hit or miss signal, because the data does not have to go through the comparator. So this can be an important consideration, because the processor can now go ahead and use the data without knowing if it is a hit or a miss. So it can assume that it is a hit, or it can assume that it is a miss. Just if it assumes that it is a hit, then it may be having a misprediction. Since the hit rate is in the upper 90% range, so you will be ahead of the game 90% of the time, and for those 10% of the time that you are wrong, just make sure you can recover. However, we cannot play this speculative game here with an n-way set associative memory, because as we said earlier, the data will not be available to you until the hit or miss signal is valid. So today we have discussed three different categories of the cache design, namely the direct mapped cache, the fully associative cache, and the set associative cache. We have also discussed the merits and demerits of these three different types. Now, with this much discussion about the cache design, we stop over here today, and next time, inshallah, we will take up how we can make use of these different types of memory organizations and what are their other applications which we can study. Thank you very much, and Allah Hafiz.